faculty in the UMA, in the Massachusetts University, from 2001 to 2008. After that, he got a professorship in University of Missouri in Kansas City. Kansas City is half in Kansas and half in Missouri.
True.
That is really weird. But
it's the city to Kansas.
And that is where he's working now. So he's going to speak us about guests for Quenching, of Galaxies. That is his topic of interest. And that's all.
Okay, thank you, Sebastian. And thank you, everyone, for having me. I had very nice discussions yesterday. I think we will have more again tomorrow. So I always like to start off a colloquium like this to give a very brief introduction. Well, first of all, why are galaxies important to study? We're talking about the growth and quenching history of massive galaxies. That's a pretty large title. So galaxies, we live in a galaxy, but galaxies are important for a number of reasons. They're the birthplace of all stars and planets and the chemistry for life. If there were no galaxies, there would be no star formation, there would be no production of planets and no chemistry for us and maybe the other life out there. They help us trace the large-scale structure of the universe so we can see the cosmic web and understand how the universe is put together, at least its skeleton. And near to what I do and Sebastian and probably everybody in this room is they are beacons, light bulbs, or flashlights to see and trace the evolution of the history. What we know about the history of the universe is mostly tied to studying galaxies, both near and far. And I've been studying the evolution and formation and the development of galaxies most of my career, going back into the late 90s, but for almost as long as I've known Sebastian. And so I have a couple fun pictures here. This is near the time we're in this looks like a torture chamber, but it's actually, do you remember the Der Kartoffel, which means the potato? This is a restaurant with all this ancient farm equipment on the ceiling. And this is one of the first meetings, I think, for the GEMS Hubble Space Telescope survey, either in 2002 or 2003. My pictures wouldn't tell me. And then here's a picture from a couple years ago. The last time I saw Sebastian at the Cosmel conference, I think Vladimir was there too, right? Were you there at Cosmel?
Yes.
One of the co-organizers, right?
Yeah, he was there.
Yeah, that was a very, very wonderful conference. All right, so to give a bit more detailed introduction, let's talk about the history. I like to say that a key observational aspect to the history of galaxies is something I like to call galactic capitalism. And so in this famous figure from a few years ago, it shows on the y-axis the stellar mass density in galaxies as a function of redshift. And you can see the quench population has a very strong evolution since at least redshift of 3 across sort of redshift 1 to 3. Sandy Faber, who I hear is visiting in a couple weeks, coined this term the cosmic high noon because the development of galaxies is very active in that short period of time. Most star formation, most quasars, AGN activity. And you see this quench population. So around a redshift of 3, oh, this thing, I knew it was do this. Okay, so around redshift 3, you can see it says 2%. So that means the quenched, dead, massive population of galaxies was 50 times smaller in mass density, total amount of stars at that time, about 11 billion years ago. And that's accompanied with a declining production of stars. And so this is a famous compilation of the McDowell plot, which is the cosmic average star formation rate density as a function of time. So redshift again on the x-axis, and this time the cosmic star production. And you can see during cosmic high noon, it's essentially flat, producing stars at a much greater rate on average than today. And the blue population was more dominant during cosmic high noon, and it was growing. Of course, it's making stars. It should be getting more of the wealth. The stars are like the stellar wealth, and yet it's growing slower, even though it's making the stars. Quench galaxies are not making stars, but they're growing faster. And then, of course, around half of the age universe, about redshift of 1, we all know that the production of stars drops by a factor of 10 to today. And basically, where stars are being continually formed today, at least in the massive population, 10 to the 10 times the mass of the sun, that population is almost essentially not growing in total mass density, even though it's making stars, and yet the dead population just keeps on growing. Or I hear everybody here call it the retired population. And so this is a sort of capitalism. The galaxies that are not making the stellar wealth are collecting all the stellar wealth. And the other ones who are the workers that are making the stellar wealth, they're not getting so much. So this is nice, and this gives a nice big picture of the growth of galaxy population and the quenching, which is the topic of today's talk. And just a little bit more introduction to set the stage. As a member of CANDELS, which I'm sure most of you have heard, this is the largest survey of distant galaxies with the Hubble Space Telescope when they added the new Wide Field Camera 3. Sandy Faber and Harry Ferguson combined forces, and I was lucky enough to be part of this huge international team to study these 5 very well pieces of celestial real estate where the world's telescopes, both on the ground and in orbit, are just concentrating huge amounts of resources. And so we have this nice statistical sample. And as part of my work with this team, I've been focusing on the morphologies of galaxies and also a little bit on the structural evolution. So just to give a quick example, this is actually the technique for doing the classifications has been published in Cartel-Tepe 2015, but this work has not yet been published. A punchline, we can take the visual classifications that the CANDELS team did, and basically we can identify objects that are spheroidal, 3-dimensionally round or kind of like ellipticals, and galaxies that have disk profiles just by the observations in the HST images. And then essentially from visual classifications, break that into 4 bins. So pure spheroid galaxies to pure disks from the left to the right, and then objects that have a disk but very large central concentration of mass in the center, call them bulge dominated, and then objects have less in the center, call them disk dominated. And I'm showing panels of these examples, objects at different redshifts from the bottom to the top, high redshift around redshift 2, 2.5, up to redshift about 0.6 to 1. So we're moving in time upwards. And essentially the punchline for massive galaxies, again, 1 times 10 to the 10 times the mass of the sun, more than 90% of the galaxies have this kind of normal, or the massive galaxies have this normal shapes and appearances. And you can combine this with structural measurements. For instance, you use GalFit to fit the surface brightness profile and get the half-light radius and other structural parameters. I'm sure Sandy Faber will talk about axis ratio evolution. And so here I'm going to show a little bit more detail of this evolution of both the quenched and star-forming population. And I'm going to use 2 new axes. In the y-axis, we have the specific star formation rate. This is compiled from UV and infrared data to get a measure. It's also similar to SED fitting analysis that the CANDELS team has done. And the x-axis, the stellar mass surface densities, basically the surface mass within a half effective or half light area of the galaxy from the GalFit. And then in each panel, so this is the highest redshift panel, that's why I've covered the other ones for a minute. In each panel, I split these 2 axes into 4 quadrants. So top to bottom, you have quenched at the top, star forming at the bottom, red and blue, and a dividing line, that gray line, which basically breaks the population empirically into the 2 bimodal populations. You even see at redshifts around 2.5. And then from left to right, more and more dense. So on the left, you call these extended, the stellar mass is spread out, and more compact is high density at the right. So compact, extended, quenched, and star forming. And now I've selected redshift bins from redshift 2.5 to redshift 0.6 in equal co-moving volumes. So you could see the increasing number density evolution of galaxies in the whole population. Again, these are massive, so above 10 to the 10. And now see how it breaks down in these panels. And so each panel, you could see just in general, forget all the details of all the points. The points are sort of shifting around, but you see more points in each panel. So you're growing number density of objects. And now let's focus on the disk galaxies, the star-forming disk galaxies. So these right here. So little symbols just represent my flat, no disk, no bulge, disk with a small bulge. Lump them all together. They tend to sit in the star-forming population at every single redshift. And then I'm going to show the evolution of this population over time, and the larger, thicker ovals mean greater growing number density. And you notice 2 things. The disk, star-forming disk population evolves pretty boring. It just keeps on having more galaxies. They stay basically the same amount of extended. Some are a little bit more concentrated near the vertical dashed line, so they have maybe starting to get a bigger central mass concentration, and then some are very extended. And their average specific star formation rate is slightly growing towards quench, so they get a little bit less productive on average we understand that because less accretion of gas. Now, if I contrast that with all the little round symbols, the spheroids, which tend to sit in the concentrated part of the diagram, you notice a couple things right away. They are mostly in all three other quadrants at every single epoch. They're mostly visually spheroidal, mostly compact at the highest redshifts up to redshift 1, and then they start to slide over towards the left to become more extended, which is this dramatic size growth that people, for instance, like Ari and Vandervelde have published. So let's look at the evolution number density of the quenched galaxies. Again, number density of quenched galaxies growing even faster is redshift to redshift of 1/2. And this evolution is consistent with, at redshifts greater than 1, something called fast quenching. What I mean by fast is basically you take some galaxies that live in the lower right-hand corner, which are compact star-forming objects. If they have a lifetime in that bin of 500 million years, and then they get quenched, they will explain the buildup in the red population for the 3 highest redshift bins. So they perfectly explain it with that very simple model. Take the galaxy, it lives there 500 million years, move it to the red population, explains the red growth. Then at the lowest redshift bin, that no longer explains enough of the growth in the number density at redshifts around less than 1. You need some of the galaxies that are in the extended blue population, the star forming, to quench slowly, extinguish, and slowly evolve to add to the red population. So there needs to be some portion, about half of the growth has to be from the extended blue population. And then you also notice the whole thing shifts over towards the left. And the theory there is that the existing compact quenched galaxies are over time having lots of little minor mergers, which build up the outer halo of the galaxy to make it more puffed up, like modern day ellipticals. Modern day ellipticals would even be farther to the left for massive ellipticals in terms of their half-light size or their density. So there's a lot going on in here. One more to set the stage. So this paper from the CANDELS team, I was part of this with Dale Kocheski. This is really interesting. So it's the same thing around redshift 2. It's the same 4 quadrants. You have extended compact, star forming, and quenched at the top. What you see in each of the quadrants, the dark red is the frequency of X-ray AGN. In the bottom right-hand corner, almost 50% of the compact star-forming objects at redshift 2 have an AGN, which is a nice coincidence and maybe an obvious explanation, or at least a reasonable cause for what's causing the quenching. And so based on that and some, actually that was a nice affirmation of this theory that came out a couple years ago by Avishai Deckel and Andreas Burkert, so-called dissipative compaction. The idea here is that galaxies in the lower left-hand corner, the extended star-forming disks, they're slowly building up in mass. So you can see they're changing from blue to green color, building up the bulge. And then something like an AGN happens to quickly turn off the star formation, and they evolve to the quenched population. So they have this fast track quenching, which is the majority of what they think as a theory would explain the growth of the compact quenched galaxies at sort of redshifts 1 to 3. So there's a lot here, a lot of ways you can think about how the galaxies are quenching, how they're growing in mass, different processes. And so I like to use concept maps to visualize this complex connection between these different key processes to help my students and even myself self-synthesize how all this is working, how it interrelates to each other. And so we're talking about 3 key physical processes. I'll show down here at the bottom with the different arrows. They're going to explain how galaxies move around in these boxes. And all processes are, of course, based on our very successful cosmological model, hierarchical. So whether you're creating large amounts of gas in stars or small amounts of gas in stars, it's all hierarchical processes that cause the things I'm about to show you. So first of all, one key process is fueling galactic activity. So you create a lot of gas, you can fuel strong amounts of star formation. You can also accrete a little bit of gas and fuel normal amounts of star formation. And if you accrete a lot of gas, you can also quickly turn on the black hole and create a very powerful AGN. Of course, this kind of fast fueling of both star formation or a powerful AGN can also quickly, theoretically, quench the star formation, whether it's AGN feedback or supernova feedback in short timescales, again, less than 1 billion years, quickly turn off the star production. So the second key process is extinguishing star production, or what we call quenching. And finally, the third process is how do you actually make these round objects, either forming three-dimensional spheroids or transforming disks into spheroids. I call this transforming or forming galactic structures. The fast process predicted by many people, for instance, a very popular fast process is major merging. It takes extended objects, smashes them together, and makes a very compact, dense, roundish object. There are other predictions, such as violent disk instability, which is featured in the Deckel-Burkert theoretical paper. Both of these are predicted, again, on fast timescales, less than a fraction of a gigayear, to make very compact, putting a bunch of the mass to the center of the object. And then, of course, and these are our three different physical processes, and we only talked mainly about fast processes, and you can already see that there's interrelationships between all three. And of course, there are slow processes. In other words, processes governed by slow accretion, slow star production. So for instance, slow accretion can cause the AGN to turn on maybe sporadically, very short timescales, maybe weak AGN, and also quench star formation, perhaps providing a maintenance to taking galaxies that are already retired, keeping them retired. And then there's something about star formation in typical disk galaxies that over time builds up the mass towards the center of the galaxy. So just a disk galaxy sitting there making stars, as you track it forward in time, the mass will tend to concentrate more and more to a bigger central mass concentration bulge, for lack of a better word. And there's at least an association between that growing of the bulge and the galaxy becoming quenched. And you even notice the quenching happens from the inside towards the outside. So first in the inside and then to the outside. And so probably many people in this room, if not everybody, are working on different or multiple aspects of this diagram, and as are my students, and there's many, many questions to answer. So just some examples to set the stage for the rest of the talk. There seems to be a connection possibly between violent merging and formation of compact objects and the triggering of AGN. And could it be hidden by dust? Because there's a controversy of whether or not this happens all the time or not. What's actually causing the quenching? This is probably one of the biggest questions in galaxy evolutions. What are the physical mechanisms, and where do they act, and when do they act, and on which galaxies and which environments that turn off star production? So that's a general question, what's causing quenching? And then, for instance, a specific question, is this fast quenching only happen in more compact objects? Maybe because it's associated with a fast and more powerful AGN or starburst, maybe because it's a compact object and so its physical size to be influenced by the center is less, who knows? And then finally, if there are different competing theories for what's causing objects to compact, or even if there isn't different ones, just understanding what is causing objects to compact. Is it merging? Is it something else? How do we identify those? How do we actually say, yes, this is an object doing that compaction process right now, so we can count them up and measure the rates, which is the most important thing. You want to understand how important a process is. You really want to understand, as a function of time, how does the rate of this process happen? So we're working, my team of students are working on all these questions. And so I'm just going to use this framework for the rest of the talk to do a couple quick examples on specific projects that are touching on these questions. And I'll start with the first question. And my team is using big surveys like CANDELS to do statistical analyses, but also using those surveys to focus, to identify weird, rare galaxies. Galaxies that have maybe a dusty AGN, or mergers. Mergers are rare in terms of their fraction of a sample. They're often less than 1%, but they might be the most interesting 1% and reveal some clues about what's happening in this whole complex framework. And so the first one, merger-triggered AGN. There's a huge debate in the literature. This is a slide that my grad student Maddie got from a friend of hers at a conference. It's a pretty cool collection. It shows on the left-hand side a whole bunch of recent papers and a few, almost all the papers are recent. There's a few original papers showing that, yes, for sure, we believe in those papers, the authors, that there's a connection. Mergers cause AGN. And on the right-hand side, there's as many papers that say, nope, You look at mergers, there's no connection. And I'm actually a co-author on papers on both sides of this, and multiple papers on both sides of this. You do notice that there's a tendency that there's a bias, or not a bias, a selection bias or a selection effect. When there is no connection between merging and AGN seen in the data, AGN are selected at shorter wavelengths. Lots of X-ray studies in blue, a few optical studies. If you look at longer wavelengths, sometimes optical, but also especially recently, I think infrared is the key, then you see a connection. And so the first thing I want to talk about is this paper from a couple years ago. My PhD student, Maddie Weston, shown here. She did a simple experiment. She used the WISE colors. This is actually started by Mike Jarrett. He was one of the 2MAS and WISE technological researchers and experts. He came up with a scheme, and other people have done as well. I'm going to show it here schematically. We have an SED over many wavelengths, so from ultraviolet on the left to far infrared on the right, and the energy output, and this is just some example galaxy and showing some components. What I want you to focus on for right now is 3 of the 4 passbands on WISE that let us measure 2 colors. So if I take star-forming galaxies, the 3.4 minus 4.6 colors are actually blue for star-forming galaxies. Well, that kind of makes sense. But then the 4.6 minus 12 colors are red because of the dusty fraction of light being emitted from, inside these 2 regions. The energy from the hot stars is heating up the gas and re-radiating in infrared wavelengths, and so you see this red color. Whereas the retired galaxies are blue in both colors, in the WISE colors. And finally, in the 3.4 minus 4.6 colors, you see this little flare of colors going to redder color. And that's from dusty AGN, basically covering that range right there. And so it's simple. You just plot color, you see the distributions of objects, and you look for the things that have red 3.4 minus 4.6 colors. And so then she applied this to a huge sample of tens of thousands of control non-merging galaxies, and then compared it to a visually selected sample of 100 very recent post-major merger kind of train wreck crash looking galaxies selected from the Sloan Digital Sky Survey, and she found a very strong increased incidence in the amount of AGN in mergers, and importantly, the amount of dusty AGN. So we're talking about AGNs that are hidden by dust that make the very red colors in the bluer wavelengths of WISE. So 5 to 17 times more likely, it's statistically significant, and much, much higher than any other subpopulation you could think about. And importantly, you do exactly the same experiment and just use the BPT analysis of the flux ratios at optical wavelengths to select CFERTs, for instance. There's no connection, no increased incidence in essentially unobscured AGN with mergers. The AGNs and mergers are at least half the time dusty, and this makes us think that perhaps all mergers have an AGN phase. Maybe it's just a short phase because the lifetimes for AGN activity is actually pretty wide error bars, a few million years to much, much longer. So the other thing is a complication. All these objects tend to be star forming. Not surprising, you're creating gas, you're feeding the black hole, AGN's going off, star formation is happening also. And there could be some contamination, and maybe it's making it hard for us to understand exactly what's happening. And so her follow-up work that she's working on to finish her PhD thesis here with a couple undergrad students she was supervising this summer is to combine other surveys of galaxies to do SEDs at least from 22 microns in the red wavelengths into the ultraviolet with Galax, and use different SED fitting codes to try to disentangle and tease out how much of the energy output in the infrared, the WISE dusty AGNs, is actually really from an AGN, how much is from star formation. And she's basically just started this. She's got about 30% through some initial analysis of 200 WISE AGNs, and she's created a pretty complicated code to do photometry of the complicated isophotes of merging galaxies. All right, so jumping back to our concept map, there seems to be this connection between merging and AGN, at least sometimes, and we think AGNs is a good physical mechanism for quenching, at least fast quenching. And so back to our question, what's the primary cause? Is it really AGN or not? And is this only, again, happening in compact objects? And there's this connection, again, between merging and AGN in compact objects. And so what we did, at least locally with Sloan, is to look for any rare compact quenching galaxies that perhaps are the remnant of a recent merger. These might be analogs of the much more common galaxies that are happening at redshifts 1 and 2 that we saw in CANDELS. And so to do this, we started by focusing on unusually blue ellipticals. So this is a big statistical sample from Sloan, over 60,000 massive galaxies. We have optical color versus mass. The gray is all the galaxies, and then we just focused on the blue cloud. And by visual classification, though these also have the structural properties of spheroids, we found the blue dots that kind of pile up close to the red population, the so-called green valley or Valley Verde. There's elliptical population. A subset of those ellipticals have a little bit of funny structure on the outside, perhaps merger remnants, who knows? And then there's even a couple of really nice, dense post-merger spheroidal objects that are very dense in the center with great big tidal arms. And at least these three make a plausible sequence that you would expect if you look at a merger simulation of right after the two galaxies collide, and then slowly the tidal features decay, and finally you have left over your spheroid, and they would be, if quenching happens, they would be moving towards the red population to build up the population. And so we actually focused on these objects. They're a very small fraction. All these ellipticals are only 2% of the high mass Sloan sample. So we're really zooming in, and we zoomed in even further by finding a special subset of these blue and open circles, which we now call recently quenched ellipticals. So what's special about them, they had everything you saw before, but they also are completely spectroscopically dead. There is no line fluxes from any H alpha, nothing, like all below 3 sigma. They also are very young. So their blue color, if you look at a spectroscopic analysis of the central light, so that is a caveat, Anna Galaxies did a study with Sloan where she could measure the luminosity weighted ages by fitting stellar populations to the spectra, to the continuum of the spectrum, and getting these very young ages. And these objects that are totally dead, turned off, no spectra, have ages on average of 3 billion years, where a normal red and dead elliptical or retired galaxy is like 9, 10 billion year old age. You can find them if you have no spectra using U minus R minus Z in Sloan. You have to be careful. It does a good job, but you still have to double check with a few things, and it's always better to have spectra. So these are what I would say the best candidates in the local universe for, we see a famous ARP galaxy like the antennae, 2 spiral galaxies colliding and merging, and we see, from simulations going way back to the Tomb rays, that we believe this is going to form a round spheroidal galaxy. So we see those kind of objects out there. Where are their progenitors? And I'm saying these are the best candidates for their progenitors. They merge together, make a round galaxy, something quenches quickly, as predicted by Hopkins, and before him, Sanders, 1988, and Phil Hopkins later on, this sort of major merger model of forming red and dead ellipticals. So these are great candidates. We could only circumstantially try to figure out what was quenching them. So the paper in 2014, we identified these, and then we looked at what are the possible quenching mechanisms, and basically we came with more questions. The most important question being, why are almost all of them moderate mass galaxies, round and dead, sitting at very small halos? So they tend to be central objects. 90% of them, at least in a statistical group catalog from Yang et al., they are central galaxies in a few times 10 to the 12 dark matter halos, which theoretically should still be accreting gas and forming stars. So what killed them off? Not sure. They circumstantially fit the Phil Hopkins model that they're at the right halo mass and stellar mass to be the product of major mergers, as we hoped when we selected them. And major mergers could temporarily quench star formation, so maybe that's it. Not much of association with AGN or post-starbursts, like a very strong starburst that could have caused supernova feedback. Part of the problem is those processes of these things were made by merger, and now they're round and pretty normal looking. That's probably 1 billion years ago, so why would there be an association for an event that happened 1 billion years ago? So a lot of open questions, and one thing we thought is we can get at the gas of the halo. If we can understand something about the halo gas around these recently quenched ellipticals, that would help give us some clues about what's going on. And so a colleague of mine, we got together and we tried to find for our 150 recently quenched ellipticals, are there any light bulbs in the distant universe, quasars, that we could use with the Hubble Space Telescope COS spectrograph, the cosmic origin spectrograph, to peer through the gas cloud, the atmosphere of the halo of our recently quenched elliptical, and look at the gas. And you might expect that, inflowing gas would explain that some future star formation is going to happen. Outflowing gas might explain some violent event, like an AGN or a bunch of supernovae. Unfortunately, too expensive. Of our whole sample, we could find 4 or 5, and it would cost us something like 300 orbits with Hubble Space Telescope. That's a no-go. The CANDELS survey over 3 years of observations was a total of 900 orbits. So we just gave up. We said, well, we can't do that. So the next thing is to look at maybe the star-forming gas. So I have colleagues in South Africa where they're building the SKA. The Meerkat is the precursor for the giant radio telescope array. And we all know that, here's a picture of a star-forming spiral galaxy, and on the right we see the 21 centimeter cold neutral atomic gas. It's sort of fuel for future star formation. Okay, we could at least use SKA to get at the gas mass around our recently quenched galaxies. We can even look at all recently quenched objects, not just the ones that are elliptical, so get rid of the subjective visual classification part. And so this first project is going to be the beginning of this, what we're calling the Quenching H1 survey with colleagues from South Africa. And I have a new PhD student, Deepak, who just joined this August. He came from India, he worked at a radio institute, he has some expertise with radio data. And so he's going to first use the larger new Sloan sample to kind of grow our recently quenched galaxy sample by 3 or 4 times and do even some more analyses, sort of follow up to my 2014 paper. And then we're proposing for time on Meerkat, on UGMRT in India, perhaps other radio telescopes to get at 21 centimeter data. If you look at radio survey catalogs, there are no RQEs in the catalogs. They're just slightly too far at redshifts 0.03, 04, 05. That's too far for the sky, all sky or part sky surveys. Of course, in the future, we hope to use SKA with our colleagues and have this be a long-term survey. For one, with SKA, we'll be able to resolve the gas, measure kinematics of the gas. We also need to talk to some other colleagues about getting molecular gas measurements for these objects as well, maybe with ALMA and so forth. Okay, for the last part of the talk, we've talked about these special cases in the local universe that we can investigate in detail. The really big questions in my mind, and where my team is spending a lot of time, is this idea about what is actually making these compact objects in the first place. How can we distinguish, for instance, major merging from something that's not major merging? And so for that, a whole bunch of my students are working on doing this with, again, CANDELS data. And so here we have a collection of master's students, undergrad students, and we are analyzing the residual images from Arjen Vandervelde. He did a catalog where he ran GalFit on all the CANDELS data. He repeated it again for HST3D. And so you can see for all the H-band F160W images, like on the left, we have an example galaxy that maybe is interacting with its companion at the top. That's a redshift 1 galaxy. We see the model from GalFit. It's just a single Sursic fit to both galaxies, takes a subtraction. Residual image has a lot of information. Faint structures like tidal features are very short-lived in time and faint to see. So removing most of the galaxy light will help us identify these features. And so we're actually analyzing this data in a multifaceted way. We were awarded a Hubble Space Telescope archive proposal a couple years ago to do all this work. The first thing is we're classifying this huge sample of 10,000 massive CANDELS galaxies, classifying the residuals and adding to the community a catalog of fit quality flags, because, for instance, the well-known paper that shows that quenched galaxies size growth by 5 times from redshift 3 to 0 is based on the sizes measured from this data. What if there's something wrong with those fits, for instance? And then more importantly for our research, we're trying to characterize the features of the residual thing and make the characterization less subjective. Yes, we have tidal features maybe, and that is subjective, but a lot of it is, is there features towards the center? Are there features that are asymmetric? So then we can actually do some machine learning to try to train on this and select these things automatically. A second thing we're doing, My other PhD, Kameshwara, Mantha here, the rest of the talk is all Kameshwara stuff. He came up with this really sophisticated software with Python to analyze this residual images to both pull out features and quantify them. The first quantification he does is just identify it and then give me the surface brightness, but he has ideas for more things to do in the future. Not going to go to details, but really quick, the left is a residual image, upper left. He masks out the center part because the fit often is a little funky there. And then he has a larger mask defined by multiple effective radii for the galaxy. Then he masks all the other sources out. He gets the background pixels outside of the annulus on the left. It's hard to see. It's a red circle about half as big as the image. That's the blue histogram on the right. And then he looks at all the pixels, flux values on the inside of the annulus. And that's the red. And he just identifies those pixels that are above the background. Then he runs another algorithm that identifies where pixels above the background, how connected are they? And then he color codes them like you see here in the lower left. So you see one structure in yellow is all connected, and there's lots of little small structures. Then he generates noise images from the data to actually identify what things are statistically connected, and essentially what's left is basically the big yellow feature and maybe a couple small features. And then he color codes that and gives us the surface brightness. And he can run this on every single residual image in CANDELS. And this paper is submitted a month ago. Haven't heard from the referee yet, but I think it'll be good. Here's just this paper was merely, this is the technique, and here's its application to different CANDELS galaxies. Nothing statistical, just examples. So here are examples of plausible tidal features from CANDELS. Every single panel, you have the left is the image, right is the residual, center is the residual, and right is the extracted feature put back on the image. And so you can see on the left, like 3 examples of pairs where either one or both of the galaxies exhibit some sort of extracted feature. And this extraction is automatically. It's not, he didn't pick the feature and say, take it out. It's just done all automatically following the process I just showed. You get broad features, you get thin features. Maybe this one on the lower right around this one object is a minor merger coming in. This might be a post-major merger in the center to the right. It's thin kind of structure. What's left for this project, and there's a lot, is he also demonstrated applying it to mock data from merger simulations. So the Vela simulation is a bunch of different time steps for galaxy evolution drawn from a cosmological simulation. It's Daniel Servino. And so he took the mock images from the merger simulation. Then we do a process we call candelize the mock image to make it look like it was observed with the CANDELS telescope, reduced, add noise, change the resolution. And so you see in the top, from 0.6 gig years before the merger of the 2 objects, they're coming together close passage, go apart, come together and merge over here on the right at t = 0. And then moving from the left on the bottom to about 0.8 gig years afterwards, the post-merger signatures, and he ran his code on all these stamps. So you can see we can extract the different features. And because we know about the merger history, we could try to come up with ways of better calibrating what we think are merger features from these zoom-in simulations. One idea is he wants to add some bells and whistles to his code to try to measure some metrics, quantitative metrics of the shape of these features so we have better automatic identification. And finally, where he and some other students are developing machine learning code to do what the visual classifiers are doing with machine learning. Cool future prospect. This is again from Vela. This is a simulation of right after a merger of a massive galaxy at redshift 3. The top panels are exactly the same picture. That's if we have the deepest CANDELS data, 10 orbit depth, you see nothing. It's just the features are too faint, the object's too far away. At James Webb depth, I think this is 20-minute integration with that camera as part of the Sears team. So we are part of one of the original awarded 13 or 14 teams for James Webb time. Hopefully it'll launch. Same object, but you can now see the tidal features. He runs his extraction. So we'll be able to try to study and quantify and identify merger features, maybe the first major merger features at redshifts around 3. And really quickly, Kameshwara supervising a senior student who's graduating, Logan here, to actually run this on Sloan and all the multi-pass bands. So to try to get colors of tidal features to say whether the progenitor of the major merger was dry merger, retired galaxies crashing together, or a blue merger, and then maybe get the mass of the tidal features, which will tell us something about the dynamics of the merger, whether it's a major merger or a more minor merger. Okay, last but not least is trying to constrain the rates. So typically we start about 12:05. I like to go like 45 minutes, so we have plenty of time for questions. So actually we'll truncate in 4 minutes because we can do more tomorrow. Constraining rates, back to Kameshwara. So to constrain merger rates, you need to identify mergers and then estimate something about time scale for how long the identification could be, and then you get a rate. And this is a nice slide that Kameshwara shows. There's basically two ways that astronomers find mergers. Either they have weird tidal features like we see here on the right, and we just learned a lot about, and he's developed codes for this, or close pairs. So you have two objects close together, no features or not, it doesn't matter. They're close together, certain defined by projected separation, a separation in redshift, a mass ratio between the primary and secondary galaxy. All those factors go into selecting pairs. And his first paper came out in January this year, published, is he's using CANDELS plus Sloan Digital Sky Survey to do the most comprehensive merger history paper to date in the literature. This is an awesome paper. It's massive. He did everything, like all possible ways you would select merger. So just for instance here, you have as a function of redshift on the bottom, just massive galaxies that have a major companion defined by some criteria next to it. And you can see for 3 different selections of how close in projection, and then he plots for the CANDELS 5 data points from redshift 0.8 over, and then the Sloan anchored on the left. And you see, no matter how you do the selection, you see the same general trend. Mergers are way less frequent today, or close pairs. It rises up to some sort of a peak around redshift 1, and then it sort of drops off or is flat, which is weird because we know that merger rates in the big cosmological simulations, the merger rate evolution just keeps on going from redshift 0 to 1 to 2 to 3, growing and growing and growing. Many more mergers it predicted in the past. So this flat merger rate, merger fraction made us scratch our head, but okay, because we thought maybe are we missing galaxies at high redshift, but we thought our sample is very complete and very well defined, all kinds of statistical corrections, analyses, but we'll do the rate. So rate is just take the fraction at every redshift, divide by some observability timescale. Simple. So here's the big plot. I'm not going to go into all the details. This just shows like his main measurement is the red points. The merger rate now is the y-axis, going up, peaking around redshift 1, turning over and sort of curving down here if you do mass ratio selection. You could also do flux ratio selection. There's a whole discussion about that, why that gives you a different answer. He compares other observations like Lotz et al. Out to redshift 1, and then you can see the merger rate by the 2 main theories. There's Rodriguez, Gomez, 2015, and Hopkins are the black and green lines going, just increasing, going out to high redshift. Let's just focus on it like this. So the main result is the pink error bar swath and the red line that goes up at redshift 1 and bends around like this. And that's if you assume a constant pair observability timescale. Completely in disagreement with the major merger rates by prediction. It agrees from redshift 1 to, redshift 0 to about redshift 1 or so, and then they just completely separate.
Sorry, what is the mass limit? Are the same in the simulation?
Yes, so 10 to the 10, the primary galaxy is 10 to the 10, or 2 times 10 to the 10 solar masses, and then the mass ratio is 4 to 1 mass ratio or close to 1, so that range. And that's the same in the simulations. So one thing that we investigated, what if you change the merger timescale? And there was a paper that came out at the same time from our colleague Greg Snyder from CANDELS, where he played a game with simulated data and showed that perhaps the observability timescale for pairs, if your sample is complete, is just evolving with redshift. And if you apply his published timescale, then you get the dashed dot line from our same exact pairs from CANDELS. And you get very nice agreement with the theory, and you get this huge difference that happens at redshifts 1.5 and above just by having an evolving timescale, which makes sense. You might think we know the dynamical timescale evolves with redshift, and this basically evolves in the same way as the observed pair timescale. And so his next project, his very ambitious for his PhD thesis, is basically to try to constrain these observability timescales for both the pair methods and the tidal methods and calibrate using observing the biggest mock data. So he's doing illustrious simulations and for, not illustrious, but another Vela simulation for tidal features and this quasar. Oh, there's some new big simulation. Universe.
DMG.
What is D? No, that's a observational study.
No, it's the illustrious high resolution. No.
Yeah, but there's one called Azar AGN something or yeah. So I forget because it's doing so many of these things so fast. And then for pairs, he's using mock catalogs from 3 leading semi-analytic models, so they can make giant light cones of mock data from semi-analytic modeling, and then from an empirical code, the universe machine, to try to pin down the observability timescale, even as a function of different things like redshift, mass ratio, separation of objects, and do this really sophisticated analysis for the rest of his thesis. I don't have time to go into that. That was what these slides were. We can talk about it later. I'm going to rush through here. Lots of simulations. The last thing, same thing, tidal features. Again, we have mock data, but much better time resolution. These are big steps between each time. We can do this like 50 times between pictures. And so you have like a movie. And then really try to get, again, at the observability timescale for whatever you're observing, something like a tidal feature. Okay, conclusions. Again, going back to the beginning, for the quenched and growth history of massive galaxies, there is this general feature that we see in the observational data, again, what I like to call galactic capitalism. The red galaxies aren't making anything, but they have all the wealth, all the stars, they're inactive. And then, of course, the poor, discouraged star-forming galaxies are just getting squashed by the capitalistic system. This general framework of growing numbers of galaxies and even the reduction of star formation agrees, and we've known this for probably 20 years now with the successful cosmological hierarchical model. Again, the hierarchical buildup of galaxies, you merge, major merging, minor merging, adding gas, whatever. Things are getting collected to make bigger galaxies. That makes sense. The amount of accretion of gas is dropping as we come towards today, and so star production is not as excited now as it was in the past. Those things make sense, but even just the difference between the red and blue galaxies is not easily teased out here with a lot of details. And so lots of questions remain. We are all working on these questions. My team is using big multi-wavelength surveys, zoom-in detailed observations, or zoom-in observations, or different wavelength observations, or different techniques for rare objects, and now applying our techniques to mock data from the leading simulations to try to improve our constraints, again, on this interplay between the physical processes that are changing galaxy shapes, fueling galaxy activity, and turning off star formation. And I will take questions.
Questions, Vladimir?
Or comments? Thank you very much. Very nice talk. I have two comments, Dan. One about your very nice summary of the key evolutionary.
The concept map?
Yeah, the concept map. One thing is that in this scheme is lacking, I think, the role of environment, especially when galaxies are satellites. When they become satellites, there are several quenching processes that can act. So I think environment, especially when galaxies become satellites,
Fair question and fair point. That's not even a question. That's a fair point. I forgot to say that these are the processes that basically you would predict to happen on central objects. Okay. So of course, satellite quenching for sure is something we know happens. It's probably more and more important from Redshift 1 to today, because now you're having these big, large groups and clusters of galaxies, and when galaxies fall into this environment, they get. I have a slide for old colloquium I call crime in the big city. So there's harassment, there's strangulation, there's suffocation, all these terrible terms, right? Okay. So I've been really focused on the central objects, and part of that is because when I first found the recently quenched ellipticals, and my colleague is Frank Vandenbosch, he's like, they're all satellites. Yeah. And he made the group catalog. He's like, I guarantee you, I bet you, almost all are satellites. We look at the catalog, 90% small
The
centers.
young category.
Yeah.
Okay, this is my first. And second comment is just about the post-merger features as a way to know what happened with these recently quenched ellipticals. In our numerical simulations of early type galaxies, we see that most of these galaxies have a very low surface brightness disk, very extended disk that is much larger than, for example, SLOAN can
Too low
detect,
surface
yeah?
brightness.
Yeah, so this could be also interesting for these recently quenched ellipticals to
In the local universe.
in the local universe to find. Of course, there are very low surface brightness, but with some techniques, as you mentioned, for the tidal features or something like that, could be interesting to see if these elliptical recently quenched galaxies have these extended
to look deep.
disks.
So we did a couple experiments for that. So for one, at the higher redshift, Guillermo Barro in CANDELS did these blue nuggets, these compact star-forming, compact quenched galaxies. They compared deep and shallow. In CANDELS, there's 2 different levels. Most of the survey has 2 orbits. Some surveys 10 orbits. You don't see no disk because people are arguing that there could be a disk. And of course, even when you have a major merger or some sort of compaction event, if there's still a lot of accretion on to this object that has angular momentum, it's going to reform a disk. And probably this is how you get things like Andromeda Galaxy. In the low redshift at RQEs, we did look in Sloan. There's a 1/5 of the sample is deep stripe 82, something called like that, stripe 82. So it's, I forget how much deeper, 3 times deeper, I think, 10 magnitudes. Not 10 magnitudes, 3 times deeper.
24, 25.
Yeah. And the interesting thing, don't see disks, but many more of them you actually see faint tidal features like you would expect from a merger. So maybe we're not going deep enough to see disks, but certainly the light we see, we did test like, is it concentrated? It is concentrated. Then we measure half-light size, and they match the half-light size mass relation of red and dead galaxies, completely separate from the disk galaxy population. But it is only looking at that light. So if your theory is true, maybe there's more light out here, but it's still very concentrated, most of the light's in the center.
Right. Thank you.
Irena?
In the merger sample, you showed an object that had like not in the outskirts, but in the inner part, like 2 nuclei or 2
For the dusty
mergers. Yeah. How many of those in that merger sample have like a double nuclei structure or double or central structure, however you want to call it?
Yeah, great question. So this one, 1 second, has to think. Oh, okay. This needs to go through this transition. This one. Is this the one you're talking about?
This one, yeah.
Okay, because I can see for sure in the upper one, there's 2. So of the sample of 100, I think it's 5 or 10% had very close nuclei that were within the single envelope of the galaxy. So you call double nuclei. I think the separation was 5 arc seconds or less. And the reason we took those and put them in there is because Y's beam is 6 or 7 arc seconds. So it would only see that as one thing anyways. So we also had a sample of pairs that were so close together, she only got 1 Y's data point, so she added that, but it was only about 5 or 10 of the 100.
Are you doing this at high redshift?
The dusty AGN? No.
Oh, you should.
But Dale did. Dale Kocheski did with the Compton thick. So of her compendium here, you see Dale is on 2 sides. So over here, a 2012 Kocheski, he has just X-ray AGN from Chandra and CANDELS, no association. Then he's right here. This is the obscured one using the Compton thick sample from higher energy. I thought it was higher energy. I don't know about that symbol, but it's Compton thick. And those would be dust obscured, and there you see that same thing.
Mm-hmm. Okay.
So that would be the one that I know that's along those lines. Mm-hmm. Doing the infrared version, oh, wait a minute. Donnelly, because Donnelly's part of CANDELS. I think Jennifer Donnelly at the bottom, 2018, I think that's using
Is this
not Spitzer, but Herschel and Spitzer,
okay?
I think, to do similar kind of game
Mhm.
with candles like Redshift 1 and 2.
Okay. Mhm. More questions? No? Well, if not,
Just a comment because there's some time. Yeah, just a comment. The question of quenching, yeah, is very central, very interesting. But I think quenching is related to the massive galaxies. Galaxies is, let's say, more massive than 10 to the 10 solar masses. So the question is, how as more massive, how they quench earlier, all these questions that you mentioned, yeah? But for less massive galaxies, the problem is not because most less massive galaxies typically are more star forming, bluer,
Still
and the problem is to the inverse. Why these galaxies delay it, they star formation?
Right.
So I think it's important to have the mass range in this kind of questions of galaxy evolution. Yeah.
See, yeah, I agree for sure. And this is definitely biased towards sort of 10 to the 10, always because it's where we still can have data and do these statistical analyses. But even in the local universe where you can go down to 10 to the 9 in Sloan, I know that if there's some fraction of the 10 to the few times 10 to the 9 stellar mass galaxies, the ones that are quenched is probably by supernova feedback. There's a Kevin Schwinski paper. So even the mechanism would be different. Whereas supernova feedback in 10 to the 10 and above just doesn't seem to happen. Think of another way, E plus A or K plus A, which are like the strongest post-starburst. That would be big bursts of stars. It cuts off. It's stopped. They're very, very rare. Even in the recently quenched, 5% of the 150 have a K plus A signature. So yeah, I agree. I'm biased to massive galaxies. Actually, the residuals analysis goes down to 5 times 10 to the 9. It's like new low. More galaxies.
okay. Irene has a question, but we also encourage to the students to ask questions.
My question is, what is happening in the tidal features that in these very faint tidal features that you're detecting? Is it star formation or?
Oh, good question.
What is happening there?
We don't know. So we, with the colors, I mean, in the prototypical major mergers in the local universe, like in the ARP catalog, for sure you see, in the antennae galaxy, which is the classic, you see definitely extra star formation happening, but also extra star formation happening towards the centers, happening in both places. The models predict that it happens in both places, maybe more towards the center. We are just trying to even find these features, because whether or not, the main thing is the features caused by tidal forces. So as the objects are coming together and they have rotation and the tidal forces in the first close passage and then coming together, it really pulls the objects apart, and that's what's causing these features. So it could just be all stars. It's just, for us, it's a hallmark signature, based on our looking at simulations of what we think is a way that this only happens when a merger happens. So if we find something like that, we can say it's a merger. Even then it's complicated. So we're not even asking the question about star formation in them or not. Some people study nearby mergers and they, tidal dwarf galaxies can be formed out of these. I mean, there's a whole other branch studying just the tidal features and the physics. We're just using it as a signpost. And even then there's complication, because you can have a big dead elliptical, a small star-forming galaxy fall in. Depending on the orbits, it's always going to get tidally disturbed, but it can cause a tidal feature that looks pretty strong, but is not a major merger. It could be mass ratio 20 to 1 and look very dramatic if you catch it at the right time. And you might say, oh, major merger, and then you're trying to identify to make your rate, and you have an error. So even using lots of simulations to try to, for major mergers, minor mergers, all these kinds of events, can we quantify these features? Everybody has merger papers and merger evolution just based on looking with your eyes. Looks weird, it's merger, I do a rate. There's lots of papers like this. I'm in papers like that as well. So yeah, that's a great question. I think that's a whole nother area of people study. The closest is my student doing the extraction on Sloan, at least to get colors of the features and then convert the color into a stellar mass estimate. But again, we're not talking about is it forming stars or not. There's lots to do.
More questions? I have a question. So in the CANDELS meeting, David could make made a very
Are you going to make a David Koo comment?
yeah, made a very uncomfortable question that
Oh, an uncomfortable question.
that I guess nobody wants to hear and nobody wants
Okay,
to
ask me.
And so, with all the observational evidence of about what we believe, and for example, this diagram that you show us about the quenching processes for the galaxies, for central galaxies, I'm talking about. So, do you think that we have like this smoking gun that leads
For quenching.
for quenching, or we can constrain the smoking gun?
So the most smoking, smoking gun is dangerous because you never want to write in your papers, it's a smoking gun. The one that seems most compelling to me, and
That's what I said. It was an uncomfortable question.
Oh no, it's a great question. That's an awesome question. It's an especially good question for students because students will see, they have a hypothesis, they see it, the evidence proves, use all these words, and you have to go in as advisor. No. Make it weaker, say it could be this, could be that. To me, this was the most interesting. And I think I pushed Dale a little for this paper because there was Guillermo Barro, like in an early CANDELS talk, like 2014 meeting, 2013 meeting, was showing his very first, he was only working with Good South, which is 1/5 of all CANDELS. And he already had the diagram like this with the compact, the quench, and he's already talking about these tracks. And they're just saying, without any evidence of what's quenching, just star forming, if you quench them, they move up just like the arrows, and you grow the quenched compact objects. And the question is, what's quenching them? And then he showed, showed this plot, he's talking about it more like, come here, it won't go backwards for me. Or whatever, like the previous plot, and he's like showing some X's for, we have some X-ray detections from Chandra, and they were all in where Dale shows in the right-hand corner, the lower. And I'm like, well, there's your quenching, right? And so then Dale went with the complete Chandra samples. And it says right there, of all those in the lower right-hand quadrant, 40% have an X-ray AGN. That seems pretty convincing. Then if you just play around with the time scale for how long the AGN lasts, maybe all of them have that. But it's easy to go from 40% to 100%. It's just time scale. So to me, that's probably the biggest. I feel like that, well, what else could it be? So I would write smoking gun. Maybe I would get in trouble. Maybe they would, referee would say, take it out.
Yes. Okay.
Dale didn't answer that question? Or he wasn't there?
No, he wasn't there, but
Okay.
Everybody was saying that.
Okay.
Well, everybody was saying, yes, we have like this kind of plots. They
Right.
actually talk about this Conceptually. They also talk about this paper. I think it's Foster Scherber. They showed
Okay.
outflows in the star forming main sequence, the correlation between the star forming sequence and outflows from NGNs. They also showed that as part of the smoking gun, and which is actually related to this. But some Daniel Katz said, I don't believe that.
That's because he doesn't like them.
Yeah. So there was a division between the people. Yeah.
That's always good, have controversy.
Right. Okay. So if we don't have more questions, let's thank again Daniel.
Gracias.
And we have after parties, some snacks.
After party.